You know, OS X has now introduced a hotkey to do that. Right, let's go. More inputs to my laptop.
You may need to plug it in.
Ah! Yeah?
It does help when you plug it in, I find. And they won.
Okay, let's do anything. Alright, one of these pages has what I'm looking for. I'm back! Stacks and queues. Stacks and queues are the two main kinds of abstract data type we talk about in this course. When we talk about an abstract data type, we are talking about some sort of thing that holds data. And we publicly describe the interface for interacting with that data. We say, these are the functions that you can use to interact with this thing that's holding your data for you. We hide the implementation. So all of the code that actually goes and does the work, everything about how that data is structured is hidden. More formally, we describe the interface in .h files. So you'll see these .h files, they'll have sort of, that did not work. Did not have the effect that I wanted. So in these .h files, we will describe the functions that actually determine how this data type can be interacted with. And we'll also, the two functions that you'll see in just about every single ADT.h file are functions that allow us to create an instance of the data type and destroy instances of the data type. There may be multiple different ways of creating it. There may be multiple methods by which we can destroy it, but there'll usually be at least one of each of these. And in this .h file, you'll also get these things called header guards. These are here just to make sure that if we have some large chain of files, one includes another, which includes another, which includes another, which includes another, we never end up in a circumstance where these functions are described more than once through the includes. So all these are here, all these do is these make sure that if this file somehow gets included twice, only the first one counts. We don't try and redefine the functions and then have a compiler yell at us saying that we've tried to define these functions twice. And then we move all of our implementation into a .c file, which actually has the structures and the code. Stacks. Very simple data structure. They are considered first in, last out data structures. That is, the first value we put into a stack is the last one we take out. There are two ways we interact with a stack in general. The first is by inserting data into it. We generally call this pushing onto a stack. So we push value in, and removing items from a stack. So we say we pop items off of a stack. If we were to take a look at the interface for a stack, it might look something like this. So we have these header guards. In this case, we have this type def. This says that whenever I say this uppercase S stack, what I'm talking about is a pointer to this thing, to this struct stack. But I don't know what this struct stack actually looks like. All I know is that it exists. But that's fine, because in order to use this, I don't need to know what it looks like. I don't need to know what its structure is. In general, when we use uppercase names for type defs, we're talking about these ADTs. So I can create a stack, I can destroy a stack, I can push a value onto a stack, I can pop a value off of a stack. There's an extra bonus, I can tell whether or not a stack is empty. So one way we might implement a stack is by using an array. That's the wrong file. So if I have this array, this is in this stack.c, this version of stack.c, I need to include the header file, so I have the prototypes. And in this case, my stack is actually going to look like a thing which contains this array and has an integer, which tells me where the top of my stack is, which element is the top. So to create a new stack, I'm just going to stack new malloc size of struct stack. You can also say calloc new and I want one of them. I can say if new is equal to null, return null. Failed to allocate memory for a stack. Otherwise we say new top equals 0. The top is the 0th element of the stack, and we return new. Then to destroy a stack, we simply free the stack. You'll see in this file I've used asserts here. These asserts are used to ensure that anyone who happens to use this library, if they don't use the function correctly, they'll get an error when they run the program, telling them explicitly that you tried to use this function and you didn't use it correctly. This is one useful way we can use assert. So s should not be null. If I want to push an item onto the stack, I simply say, well, there's another issue here. This function won't work if the stack is full, and this stack has a maximum size. Num squares. So if this stack is full, top is equal to the maximum number of elements, then this sort of breaks. There's nothing I can do. But if not, we march on and we say that our top is now equal to the value, and we increment the top. If I want to pop an item off of the stack shouldn't be empty, so I can say assert not stack is empty, and I can return int value equals s elements s top. So I move the top down one and I return the old top. And then simply to tell if it's empty or not, I would say s top is equal to 0. There's nothing in the stack. So that's how I could implement a stack with an array. Nice, fast, pretty easy to use. However, there is this problem I have, in that there is some fixed number of elements this array can have. I could make it bigger, but that's the size of this stack is defined by me. And if someone comes along and wants to use this and is ignoring completely how I've implemented it, they don't know that this maximum exists. They don't know what it is. So maybe one day it'll just break on them and stop working. So another way we could implement a stack is with a linked list. So if we go back over to our code, we can see I've defined a few useful functions here for lists, for nodes specifically. I have a new node function, I have a new nil function which gives me nothing. I have a destroy node function which will take a node and destroy everything it's attached to. I also have this weird explode node function, which is a useful tool but may not be immediately obvious. What it does is, because functions can return values by copying them out of a function, I can actually copy a whole struct out of a function. So node explode takes a node, stores all of the values inside of it into a struct, frees that node, and then gives and copies the whole node out into my function. So what I can do is, with one function call, take both the value that was in the node and the thing that it pointed to and free the node, which might be useful. And so I have this stack that uses a list instead. To create a new one, I simply stack new equals malloc. Once again, malloc or calloc, one size of struct stack. If new is equal to null, return null. Otherwise return new. And then I want to say that the top is equal to null. I have an empty list. I could also just say null there. If I wanted to destroy a stack, first I must destroy everything inside of the stack. So I can say destroy node s top, and then just free s. So I destroy all of the list, then I destroy s, because if we look at list.c, this works by destroying every single node when I call destroy node. If I want to push an item onto the list, I can say node new top equals node new node value s top, and then if new top not equal to null, because that could fail, I guess we should sort of just kill the program if it fails. So I create a new top, I put the new value in it, and I set its next to be everything else. If I wanted to remove an item from the top of the stack, I could do something like this. What was it called? Explode node. I can say s top s top equals equals top dot next. And then is empty is simply s top not equal to null. So we have a very simple implementation of a stack using linked list. Both work the same, but our linked list does not have the limitation that it has some fixed size. It just keeps going until we run out of memory. Next up, we have the queue. Queues are a first, yes?
Sorry, when do you use calloc instead of malloc?
Calloc makes sure that whenever I get memory from calloc, it's all initialized to 0.
So does that mean that you don't have to initialize
Assuming that 0 is a sensible value for everything, yes. Queues are first in, first out. The first thing we put into the queue is the first thing we take out. So queues have a front and a back. Things go in the back and they come out the front. We say inserting into a queue is to join the queue or sometimes to enqueue, and removing things from the queue is to leave the queue or to dequeue. We could implement queues once again with an array. This one gets a bit fiddly. So our queue looks something like this. We create a queue, we destroy a queue, we join, we leave, we check if we're empty. Our array version, we have the array, the front and the back. Queue new equals return null if we don't manage to allocate any memory. Otherwise we say that new front equals 0, new back equals 0. Front and back are in the same position. Whilst I'm thinking about it, I'm going to do the queue as empty. So we can say the queue is empty if queue front is equal to queue back. So, to destroy a queue, we simply free the queue. To join the queue, we would say that queue back, queue elements, queue back equals value, queue back plus equals 1. And we have to make sure that the back wraps around to the front when we get to the end. This means that we don't have some fixed number of things that we can have in the entire lifetime of our queue, but it can sort of fill up and get used up as we go through using the queue. To do that, we simply say that the queue back modulo x elements. So if it gets to the end, it wraps around to the front. Leaving the queue, we'd say that queue elements we do the same thing with the queue front. Return the value, go around again. And that is our queue implemented using an array. This version might also be called a ring buffer because it sort of goes around in a ring and buffers things. And of course, we can implement queues with linked lists. In this case, we have a front and a back. To create a new queue, once again, queue new is equal to collect one size of struct queue. If that fails, we pass the failure on. Otherwise, we say front and back are empty. and we return the new queue. Let's just steal this from here. In this case, queue is empty is simply saying that there is nothing at the front. If I want to destroy a queue, first I must destroy the list. So I destroy queue front. That should destroy everything, including the back, and then I can just free the queue. If I want to join the queue, I'm going to have to take something and add it to the front. So I would create a new I would say node front equals new node value queue front if front is null out of memory. Otherwise we can just say that queue front equals front. Actually we add this to the back, don't we? Wait, where do we add it to? Add it to the back. We add it to the back, don't we? Sorry, I'm just stuck remembering how this works. So it points to the next thing in the queue? No. We would have to say I have gotten this wrong. This points to nothing because it's going at the back. And instead what we say is if queue stab back is not equal to null. What? Oh. Queue stab back is not equal to null. So if there is something at the back, we say, what is this complaining about? Oh, it's not. We say queue back next equals back. So the new back we've created. And then we say queue back equals back. So we add it onto the end. Otherwise it means that the queue is empty. And we say queue front equals back. Queue back equals back. You'll notice I have queue back here twice because no matter what happens, this should become the back. So what I'll instead do is stick that down here and only have it once. That's how we join the queue. We create a new node, we put the value in it, and we get the last thing in the queue to point to that. We want to leave the queue, we take the thing from the front. So we simply say struct node front equals explode node queue front, and then we can say if back is queue front equals front dot next, and we say if the back was equal to the front, no, sorry, if front dot next is equal to null, this indicates that there was only one thing left in the list, and thus we have removed it. We would say queue back equals null. So we take the thing from the front and we return the value from it. I think that's right. The thing to think about with all of these linked list examples is Does it work if the thing is empty? Does it work if there's one thing left in the list? Does it work if there's any number of things currently in the list? I think this works if it's empty, by asserting that it's not empty. It works if there's one thing in the list, because we take it, then it equals null. Back should have been the thing. Yeah, I think that's it. That's how we would do a queue using a linked list. You guys have any questions about weird techniques used here, how to do this stuff with queues and stacks?
What kind of questions are we asking about?
I know the answer. I don't know if this is the official answer, but this has been the answer to most of the other questions that people have asked like this. You might need to know it to be like a distinction/HG student, and there might be a question on it in the hard one. Like your Andrew Taylor said to every single question of like, do you need to know about sovereignty? It's unlikely that you would need to.
It's unlikely that if you're aiming to just pass the course, you would need to know this.
Like there might be one of the hard questions that involves this.
Yeah, this would probably be in the harder section of questions. This should be something you're familiar with. We would expect students aiming for an HD to be able to write one of these functions. Not necessarily, you shouldn't be worried if you don't think you could write one of these on the spot. It's probably not going to affect your ability to pass the course. With that, speaking of sorting and searching, I'm going to head on to Jashank to talk about sorting and searching.
And in that order.
So Andrew Taylor's official answer is, my advice if you're worried about passing the time on the above topic, if you want to